we will end this afternoon with the presentation of the Professor de Mello about upper triangular matrices, grading, involution, and image of polynomials. Professor de Mello, are you ready?
Yes,
okay.
I will try to share screen.
Okay. You can start.
Just a minute. Everyone can see the.
Okay. Yes, perfect.
Okay. Okay, so thank you. I would like also to thank the organizers for the invitation to give a talk in this nice conference. This talk is about upper triangular matrices in two different directions. In the first part, we will talk about gradings and involutions. Actually, we are interested in describing the so-called homogeneous involutions. And in the second part, we are interested in images of multilinear polynomials. So these are two distinct subjects, but since they are since we are dealing with the same algebra, I decided to do it in the same talk. Okay, so the first part is about homogeneous involutions on upper triangular matrices. It's on this paper of arXiv. If you want to see, it's on arXiv today. Let me just post it on arXiv. To talk about the subject, we need to talk about gradings, later on involutions, and relation with these two structures on algebras. So for us, G will be a group, F will be a field, and A be an algebra over the field F. Here, algebra for me means an associative algebra. Okay. We say that a G grading on an algebra A is a vector space decomposition indexed by elements of this group G. I'm working with group gradings, okay? Only group gradings. Satisfying this property that the product of the algebra has a nice behavior with respect to the product of the group, okay? And the elements of these components will be called homogeneous of degree G, and we will denote them by this way, okay? Another important object here is the support of the grading, which is the set of elements of the group which have non-zero components. Okay. To give some simple examples to start, we start with the trivial grading, which is the one in which you put the whole algebra in the neutral component. Here I'm denoting by E the neutral element of the group G, and all other components are zero. So this is called the trivial grading. Another important example of grading is here I'm considering the set of one-variable polynomials, and it's graded by the group of integers in the natural way. The homogeneous component of degree K is the generated by the subspace generated by the x to the k. So are the polynomials of degree k. Okay, and the negative ones are zero. So these are simple examples, but we are more interested in examples in matrix and upper triangular matrices. Matrix algebras and upper triangular matrix algebras. Okay, so we start with some examples on matrices. For 2 by 2 matrices, we can consider this grading by the group Z2, given the following way. The component 0 is the set of diagonal matrices, and the component 1 is the set of 0 diagonal matrices. So you can easily check that if you multiply elements of component 0 with themselves, or component 1 with themselves, we get an element of this type, diagonal matrix. And if you multiply elements of different components, we get an element of this component. Okay, so it's a Z2 grading on 2 by 2 matrix algebra. This is a particular case of a more general grading, which we can define this way. The component now by the group Zn, n by n matrix, this is the same n, where the component T is the set in which we put the non-zero entries only in this, let's say, 2 pieces diagonal here. Okay, the non-zero entries come from here. When you finish the column here, we start again here, 2. Okay, so it's clear that the sum of these guys equals the whole n by n matrix algebra, and it's simple to verify that it's a grading. Okay. Again, this is a particular case of a more general example of gradings, which are the elementary gradings. Okay. To define an elementary grading n by n matrix algebra, we need an n tuple of elements of the group G, and we set the component of degree G as the linear span of the matrix units Eij, such that this I and J satisfy this condition. It may seem a little confusing, but if you do a little sketch here, if you put this n tuple here and here, in the columns and the rows, and you consider here the Eij, which is the degree of this guy, is here we have Gi, here we have Gj, the degree of this Eij equals Gi minus 1 Gj. Okay, here I'm using multiplicative notation, but in the previous case, if you consider here Zn with the additive notation, so instead of product we have a plus, instead of inverse we have minus. So in the previous case it's Gj minus Gi. Okay, so here the entry here is 1, t plus 1. The next one is 2, t plus 2, and so on. When you do the difference of these guys, it's always t. So this is the t component. Okay, so this is a particular case of what we call elementary gradings. Okay, actually you can define the same way elementary gradings on upper triangular matrices, which are the object we are going to give our results here. But the important thing here is first for matrices, a degrading on n by n matrix is elementary if and only if each matrix unit is homogeneous. Okay, and in the case of upper triangular matrices, we have that any degrading on it is graded isomorphic to UTN with an elementary grading. Okay, so when dealing with upper triangular matrices, we are considering always that the grading is elementary. Okay. Also, in this case, here we can see that with two different tuples, we can get the same grading. If you consider, instead of this, if you consider G, G1, G, G2, translate each element by G, you get the same grading. So to avoid this kind of problem, we may define a grading with an n minus 1 tuple. Okay. If you get an element of this, by defining that the degree of I plus 1 equals Gi. Here we have the diagonal entries. These elements here, if we define the grading of these guys, I have the grading of any other element of any other matrix unit. Okay, so this is what we are doing. We are going to define a grading by this n minus 1 tuple of elements of G. Okay. Well, now about involutions. If A is an algebra over a field F, a linear map phi is an involution if it is an anti-automorphism of order 2. Anti-automorphism means a bijective map satisfying this. Okay, that is almost homomorphism, but we inverted x and y here. And order 2 means this, that the phi is its own inverse. Okay, in particular, with this condition, we have that phi is a bijective map. Okay, some examples of involutions on some important algebras. In the algebra of quaternions, we have seen here in the mini course of Professor Del Duque, the conjugation map is an involution. Okay. Another example, on n by n matrices, we know that the product of the transpose, the transpose of the product of matrices behaves this way, so it's also an involution. There's another important involution on 2 by 2 matrix of even order, which is the symplectic involution, given this way. And the case which will be more important for us is the case of upper triangular matrices, that we have this reflection along secondary diagonal. Okay, we will denote it by this circle here. For example, if you consider here A, B, C, D, E, F, and we apply this map, we are going to reflect along this diagonal. So here will be F, E, C, and D stay fixed. We will get B and A. Okay, just for you to know what we are going to use here. Okay. Okay. On matrix algebras, there is this proposition which shows that we can, let's say, compare an involution with the transpose involution. Okay, that is, any involution can be given this way for some invertible matrix P. So we depend only on an invertible matrix P and on the transpose map. How to prove this? Well, it's simple, because when you consider the composition of two involutions, particularly two anti-automorphisms, actually, in particular two involutions, we get an automorphism. And automorphisms of this, by this column-netter theorem, are inter. So there exists an invertible matrix Q satisfying this. Okay, applying the transpose map in both sides of these equations, we get, applying the transpose map here, we get this, and here we need to invert the order of the product, So we get this here, okay, which we can, up to changing names of matrices here, write it this way. Okay, so it can be given this way, was the first assertion. Now we need to show that this matrix P needs to satisfy this property. Okay, how can we do this? Well, I know that the transpose of, the involution has order 2, so this equals A. So A star is equal to this. So first I apply this, then I apply star again, and the star is just to multiply on the left by P minus 1, on the right by P, and transposing the element. So we get this. Okay, and opening this, distributing the transpose, we get this. Okay, now, so A equals this guy. I will use that the inverse of the transpose is the transpose of the inverse, and I will get this equation. P minus 1 P transpose equals P minus 1 P transpose A. Okay, and multiply by the inverse of this on the right, so that it came to here. So this guy commutes with any matrix A. So it's in the center of n by n matrices. So P minus 1 P transpose is a scalar matrix. And in particular, the transpose of P must be a multiple of P itself. Okay? By applying this twice, we get the P equals alpha P transpose. Now, again, let's substitute P transpose here. It is equal alpha P. So P equals alpha square P. So this alpha must be plus or minus 1. Okay? So the transpose of P must be equal P or minus P. It's an interesting exercise to show that the minus case can occur only if n is even. Okay. want to try this, it's an interesting exercise. Okay, so we proved this proposition, but actually, if you see the proof we have just presented, we only used from this algebra the fact that it's actually we used the transpose evolution, of course, but we only used that the automorphisms of these algebras are entered. Okay, so actually we can do in a more general setting that if any automorphism of a given algebra is entered, for any two involutions in this algebra, we can relate them by this equation, where P satisfies this. It's symmetric or skew symmetric with respect to this involution circle. Okay. In particular, it's our corollary. It holds also for upper triangular matrices. Okay. Now the involution we are fixing here is the reflection we have mentioned before. Okay. Now we talk about graded involutions. What is a graded involution? If we have a graded algebra A, we see that an involution is a graded involution if it fixes homogeneous components. Okay. Well, why I'm defining this? This is an important object, an important structure, because it was used to classify gradings on Jordan and Lie, some classes of simple and Jordan Lie algebras. Okay, how this was done? By considering the set of symmetric elements with respect to this involution, we have that this is a Jordan algebra, and this guy will be graded. Yeah, this will be graded if and only if the involution is a graded involution. The same for the set of skew symmetric elements. It's a Lie algebra, and it's graded if and only if the involution is graded involution. So it's important to study this kind of involution, at least because of these examples, of these applications. Okay. Also, the description of graded involutions. So the description of the graded involutions on matrices were given by Baturin, Shestakov, and Zaitsev in 2005, where they worked with these problems of gradings on simple Lie and Jordan algebras. And for the case of upper triangular matrices, it was given by Valenti and Zaitsev in 2009. Well, but if you consider the most simple example we give here of grading on n by n matrix, which are the elementary gradings, and you consider the most simple involution we have here, which is the transpose, let's see what happened. Let's compute the degree of the transpose of a homogeneous element of this type. Okay, the transpose of this is this guy. The degree of this guy equals this, which is the inverse of this, which is the inverse of the degree of the EIG. So the transpose map inverts the degree of elements when you have an elementary grading. Okay, so this, since this is a very important example, we believe it's important to give a definition about this. So we say that an involution is a degree inverting involution if it satisfies this property. Okay. So the description of the degree inverting involutions on matrices were given by matrices and upper triangular matrices were given first by Fonseca and myself in 2018, and also by Fonseca, Santullo, and Yukihide in 2020 in a more general setting. Here, these Fonsecas are not the same, okay? So this is the kind of, there are important examples or more than the matrix algebra where this appears, okay? Right. So we are interested now in the case that generalize the concept of degree inverting and graded involutions, which we are calling homogeneous involutions. So if you have an algebra A with a grading and this map theta, or a bijection of the support of the grading, we say that an anti-automorphism or an involution is theta homogeneous if it satisfies this property. Okay. let's see, if this theta is the identity map, we are saying that the component G is taken into the component G. We have the graded case. If this theta is the inverse map, then the component G is going to the component G inverse. So it's the degree inverting involutions or anti-automorphism. And in this case, we can consider a different map, which is not the identity nor the inverse. So we're calling them theta homogeneous. Okay? And we say that an anti-automorphism or an involution is homogeneous if it's theta homogeneous for some theta. Okay? And the problem here is to describe the homogeneous involutions on full and upper triangular matrices. Okay, here full, I will maybe in the next conference. It's still a project. We don't have results about this, but for upper triangular matrices, we have a complete description of these theta homogeneous involutions. Okay. To do that, first we consider homogeneous automorphisms of upper triangular matrices. I mean automorphisms which preserve the, which satisfies that property, right? Okay. But now automorphism, not anti-automorphism or involution. Automorphism first we are considering. So these two lemmas show the following. First, that the neutral component is preserved by a homogeneous automorphism, and that if this is an automorphism, okay, we know that any automorphism of upper triangular matrix is given this way. Then, when we apply it to a matrix unit, a diagonal matrix unit of this type, we know it's KL entry. It's given by this guy, where these P's are the entries of the matrix P. Okay? Why are these two lemma useful? Because with them, we can prove the theorem that any homogeneous automorphism of upper triangular matrices is graded automorphism, that is given by a conjugation by homogeneous matrix. Okay? How can we prove this? Well, I will use these two lemmas to prove this theorem. I will consider the following. Let's assume that the degree of EKL is not E, okay? But I know that the degree of EKK equals E. By this, if we apply phi of EKK, its degree is also E because of the first lemma above. Okay, so its KL and tri will be PKL over EKK. But the KL and tri is not the neutral component on the one hand, but on the other hand, it must be in the neutral component. So the only possibility for this is when PKL equals 0. Okay, so what's the conclusion here? Is that if you consider an automorphism, which is homogeneous, this matrix P, which defines the automorphism, has in its positions KL such that the degree is not E, and tri equal to 0. In other words, the only non-zero entries of the matrix P are the ones in which we have neutral component. Okay, so it's a homogeneous matrix. So this is a homogeneous automorphism. So this is a graded automorphism. Okay, it takes components G and components G. Well, now we use this theorem to prove a more general, to prove a similar result for anti-automorphisms. For anti-automorphism. So we have this proposition. If this is, we know that any involution or any anti-automorphism on OTN is given by this way for some matrix P, and we know that using the theorem above, that this is possible only when P is homogeneous of degree and the reflection evolution is homogeneous. Okay? So let's read again. this proposition is saying that an anti-automorphism phi, which we know we can describe this way, is homogeneous if and only if the matrix P is homogeneous of degree E, and this is homogeneous. So we notice, so to understand when some anti-automorphism is homogeneous, we just need to understand what happens with this involution. Okay? In particular, this proposition is saying that there exists a homogeneous anti-automorphism for the algebra of upper triangular matrices, if and only if this guy is homogeneous. Okay? So, when we consider that we have a theta homogeneous map, a theta homogeneous involution in upper triangular matrix, we get these two properties. This is almost saying that this theta is a group automorphism, but here we not necessarily have the structure of a group, and this holds not for any G and H, but not only for the ones satisfying this property. Okay. With this, we are able to prove this main theorem, which characterizes when the cases in which the gradings for which this involution is homogeneous. Okay. To do that, we need to understand how are the elements of the support. So here I am assuming that the grading is defined by an n-1 tuple of elements of G. Okay. And we have that the support of the grading is the set of elements of this type for some I and for some J. And the neutral element, of course. Okay. Okay. Using this fact, we show that the canonical involution is homogeneous for G-graded structure here, if and only if every time we have two elements of the support equal, then we must have these two corresponding elements also equal. So that's the condition we need to this involution, this reflection evolution to be homogeneous. Okay. Well, when we stick to involutions, the only difference is that we may the map phi may be written this way, where P is homogeneous of degree 0 and satisfies this condition. Okay, the last condition still needs to be considered. Okay, well, what we have from this, that assume that this is an involution which is theta homogeneous. Okay, this the reflection evolution is theta homogeneous. Since any other anti-automorphism or involution is a composition by this with a graded automorphism, then we have that an arbitrary homogeneous anti-automorphism or involution is theta homogeneous if and only if this is theta homogeneous. Okay, this means that once we have the G-grading structure fixed on the algebra of upper triangular matrices, the type theta of the homogeneous anti-automorphism is completely determined. I mean, if you have that one homogeneous involution, if you have one homogeneous involution, which is degree inverting, for example, then any other homogeneous involution on this algebra will be degree inverting. If one homogeneous involution is graded, any other will be graded too. If any is of this type theta, any other will be also of this type theta. Okay, so this is the main result of this first part of my talk about gradients and involutions. Okay, now I'm going to the second part, which will be about image of polynomials. So this is also an archive, and it's accepted for publication in this Israel Journal of Mathematics. Well, before I start saying about images of polynomials, we'll briefly talk about polynomial identities and central polynomials. Okay, so here we are fixing a set X, infinite countable set, and this will be our variables. Okay, and we consider Fx the free associative algebra. This is the algebra of polynomials in these non-commutative variables. Okay. So the definition of polynomial identity is the following: a polynomial f is a polynomial identity if, for any substitution of variables by elements of the algebra A, we have 0. Okay, any substitution vanishes. Okay, when A has when A admits a non-trivial polynomial identity, we say that A is a PI algebra. Okay, or polynomial identity algebra. For example, every commutative algebra is a PI algebra because it satisfies the commutator, this identity. Every finite dimensional algebra is a PI algebra, particular matrix algebras, okay, because they satisfy some standard polynomial identity, which is standard, I mean this polynomial here, which is alternating and multilinear in variables. And the case we are dealing with is the case of upper triangular matrices. It satisfies this identity. The product of n commutators equals 0. It's simple to verify this because when you have a commutator of two upper triangular matrices, it has 0 diagonal. Okay, and when you multiply two matrices of this type, you get a matrix with two zero diagonals. Okay, when you multiply it another time by a matrix of this type, you get another 0 diagonal here. You get another 0 diagonal here, and each time you multiply by a matrix of this type, you obtain another 0 diagonal. Okay. So when you do it n times, you get 0. So this is why this is an identity for upper triangular matrix. And we will show soon that actually this is essentially the only identity of this algebra. Okay. Well, when we talk about PI algebra, we have this set, the set of all identities of A. It's an ideal of this. It's simple to verify this. It's an ideal of the algebra of polynomials, and it's closed under substitution of variables by other polynomials. If you have this is an identity, then if we replace x by another polynomial, each x by another polynomial, we still have an identity, of course, right? So an ideal with this property, an ideal of this algebra with this property will be called T-ideal. Okay. We can also talk about the T-ideal generated by some set. So if we have a set of polynomials S, we define this set here as the smallest T-ideal containing S. Okay. If we have for some algebra A a set S satisfying this, we say that S is a base for the identities of A. So one of the main problems of the theory of polynomial identities was to find a finite set for a given algebra. And it was proved by Kemmer that it's also it was proved by Kemmer that there always exists a finite basis for identities of a given algebra in characteristic 0. Associative algebra, okay? Okay. But to find one such base is a very difficult problem. For example, for 2 by 2 matrices, it's well known that they can be generated by these two polynomials. Okay. Standard 4, that's the polynomial I have just defined, and this polynomial here, which I will mention later. But for n by n matrices with n greater than or equal to 3, we don't have a solution to this problem. Even we know there exists a finite base, we are not able to present such a finite set. Okay. Actually, for finite, there are some results, but for infinite fields F, it's not possible. Well, and for upper triangular matrices, we have that the base is generated by only one polynomial, which is that polynomial we have just mentioned in the examples. Okay. Well, another important kind of polynomials are central polynomials. So we say that a polynomial f is a central polynomial for an algebra A if it assumes, for any substitution of variables by elements of the algebra A, it assumes central values. Okay? So any substitution will get an element in the center of the algebra A. Okay? So, for example, for 2 by 2 matrices, this is a central polynomial. Okay? This actually is saying that this is an identity, right? Because if this is a central polynomial, means it commutes with any other matrix. So, when we commute with any other matrix, we get an identity for 2 by 2 matrices. Okay? So why this is central polynomial? When you have a commutator of 2 matrices, it has trace 0. So it's a matrix of this form. And when we square it, you get scalar matrix. And scalar matrices, multiples of the identity matrix, commute with any other matrix. Okay? For the case of upper triangular matrices, we don't have central polynomials other than the identities. Okay? And there is this important result of Razmislov and Formanek that shows that for any n, there are non-trivial central polynomials. Non-trivial, I mean central polynomials which are not identities. Okay. This is from the 70s, 72, 74, I'm not sure. Okay, now we will talk about images of polynomials and having in mind these examples of central and central polynomials and identities. Okay, so if you have, I'm writing here for the particular case of n and k times k matrices, but we can consider an algebra A, any algebra A, right? So, given a polynomial in m variables, it defines this function, this map. What this map is doing, it takes an m tuple of elements of your algebra and evaluate them in the polynomial f. So we get an element of your algebra A. So the question here is, this question is attributed to Kaplansky. Which subsets of matrices are image of some polynomial? Not a specific polynomial, but for some polynomial. So that's the question we are interested in. So let's see some examples. If we consider this polynomial here, then the image, of course, is the whole algebra. I'm considering here on mk of k. This is the most important case, and these are the examples here. Later, I will talk about the upper triangular matrix. So the image is this guy. By the Dimitrov-Levitsky theorem, we know that this polynomial here, the standard polynomial of degree 2k, is an identity for k by k matrices. So any substitution of variables by elements of our algebra vanishes. So the image is 0. Okay. Another important result here, first given by Schott and later for a more general case by Albert and Luckenhaupt, that the image of the commutator on k by k matrices is SLK, the set of traceless matrices. Okay. And this just mentioned examples in the previous slide, that the image of this polynomial are the scalar matrices. The scalar matrix we are identifying with the field here. Okay. Set of matrices which are multiples of the identity matrix. So we have this 4 examples here. Let's stress them, which will be important later. What can we say about the structure of the image of a given polynomial? First, it's invariant under conjugation by invertible matrices. How can we prove this? Well, any polynomial is a product of the linear combination of monomials, right? So if we conjugate a monomial by a matrix P, here you can consider that these are already substituted by some matrix or some elements of the algebra A. It's the same as doing this. Right? So in particular, for a polynomial f, when you conjugate this by a matrix P, we get this. So it still lies in the image of the polynomial f. So this guy here must be invariant under conjugation. Okay. Another important fact is that if your field is closed under D roots, and your polynomial is homogeneous of degree D, then this is invariant under scalar multiplication. Okay, so the particular case we are going to deal with is the case of multilinear polynomials. So this proposition is trivially checked. Okay, so it's also invariant under scalar multiplication. So one can ask, what about the sum of two elements in the image? Are they still in the their sum still in the image? So actually, this is asking if the image of a polynomial is a vector space. Okay, since scalar multiplication have already been considered before. So we restrict this problem to multilinear polynomials. Okay, so is the image of a multilinear polynomial a vector space? It seems a silly problem to show that something is a vector space, but it's not. It's quite difficult to prove this. And now we're going to see some examples or counter examples of these problems. Okay. Before that, it's not difficult to prove that the linear span, not the image itself, but the linear span of the image of a polynomial is a Lie ideal. In the case here, I'm dealing with K by K matrix, okay? And the Lie ideals of this algebra are already known. It's a theorem of Hairston that say that the Lie ideals of K by K matrices are exactly these four ones. Okay, maybe you can remember them since they appeared as image of some polynomials here in our examples. Okay. And if we consider the conjecture of Lvov that a multilinear polynomial has image which is a vector space, the linear span of a vector space is itself, right? So we can consider that the linear span of image of F is one of these, and with that we have the now called Lvov-Kaplansky conjecture that says that if F is a multilinear polynomial, then its image is one of the following subsets of K by K matrix. In particular, each of these are subspaces. Okay. The question is, are there known results about this? Well, yes, but before that, let's see a counterexample when the polynomial is not multilinear. Okay. So the algebra I'm considering here is K by K matrices, and the polynomial is x to the k. Okay. So if we evaluate on this matrix unit EII, we have itself. If you evaluate in the sum of these two matrix units, you also have this itself. Okay. So in particular, if it is a subspace, the difference is still in the image. So in particular, we obtain that this is in the image of the polynomial f. Okay. But this holds for any I and j, and if it's a subspace, the linear span will be everywhere. Okay? So the linear span of the image of F is the whole matrix algebra. Now, let's see that it cannot be, when we remove the linear span, we cannot obtain what we want. Let's see. So if this is in the image, what can we prove? for some I different from J. Well, if it's in the image, it's of this form, because this is the polynomial, for some A. Okay? But this element here, since I is different from J, it's nilpotent. So A is also nilpotent, but the nilpotent elements here are of index bounded by K. So A to the K equals 0. So this is 0, a contradiction. Okay? So this guy here is not a vector subspace of K times K matrices. Okay? What we know, what results we know about these problems? Okay? For 2x2 matrices, there are these results of Bello, Mello, and Rowan. For the case of quadratic polynomial by these three authors, they prove the conjecture is true for 2x2 matrices. Okay? And Malev proved it for the real field of real numbers. Real field, for the field of real numbers. Malev also proved for arbitrary fields, but we have only this condition here. Cannot prove it's only this form. Okay. For 3x3 matrices, the same authors have this nice result, which shows that the possible images are this and this. Okay. A dense subset of SL3, a dense subset of M3. Here, dense with the Zariski topology. Another set, they define the set of 3 scalar matrices and 3 scalars plus 3 scalars matrices. In each of these, there are examples which are not subspaces, but they show that these are all possibilities, but the ones which are not subspace, they haven't shown that they are actually the image of some given polynomial. So the problem if the case 3x3 matrix is true is still open. Okay, so this result is very interesting for now. Okay, other results, other known results. For multilinear Lie polynomials, Spenko proved it that the image is always SLK, and the polynomial has 2, 3, or 4 variables. These two authors, Duquesne and Clapp, in 2016, proved for 3 variables polynomials for matrices of even order, arbitrary, and some cases of odd order. Here we have about. Also, there are some variations of these problems. Messiaen proved that the image of polynomials of degree 3 always contain the K by K matrices. And he conjectured that the same holds here for more variables polynomials of more variables, if they satisfy this condition. Actually, this condition may be improved in this conjecture, but it was not in his paper. Later, Bulzinski and Stanley proved this conjecture of Messiaen for 4 variables polynomials. Actually, their proof has an error, and my master degree student Pedro Fagundes has corrected this error. It's not a simple correction, so it took some time to solve this problem. But the problem is still true. And any other there are other variations of this problem. For example, you can consider an associative algebra, or a Lie or Jordan algebra, an algebra in your favorite variety, and ask if the image of a given multilinear polynomial is or not an identity. Okay, actually, this problem in this generality is easy to show that is not true. Okay, there are examples in subalgebras of upper triangular matrices which are not in which there are multilinear polynomials whose image are not subspaces. But if you maybe restrict this for simple algebras, it seems to be more possible that a problem of this to be true. So people are investigating images of polynomials on simple Lie algebras, simple Jordan algebras, and so on. Well, now in other variations we can mention here, for example, images of Lie polynomials evaluated on SL2 have been described. Images of Lie polynomials multilinear, okay, of degree bounded by 4 on these algebras have been studied. Also for Jordan polynomials on the Jordan subalgebra of symmetric elements was studied. Here an interesting example of the rock, paper, scissors algebra. There's also interesting results. This important result of Malev for the quaternion algebra. In this case, he proved that the image is either 0, real numbers, or the vector quaternions, which are the ones which the real part is 0, or the whole algebra. Okay. And other variations here for other algebras. For example, I will mention here the subject of this talk, which are upper triangular matrices. So with Fagundes, which was my master degree student, we obtained that multilinear polynomials of degree up to 4 on upper triangular matrices were described here. Actually, I will not use this notation. I will use a different notation. Let's call by J the Jacobson radical of the algebra of upper triangular matrix, which is the set of strictly upper triangular matrices. Okay. So we proved here that, let's use this notation, that the image of a polynomial of degree up to 4 is 0, the whole algebra, or J or J squared. Okay, J squared, we will get here another diagonal of zeros. Okay. We proved also that the linear span of this must be, let's again change the notation, J to the R for some R, J to the R to some R. And Fagundes proved that for the algebra of strictly upper triangular matrices, he proved that the image is always a subspace and is always a subspace of this type for some time. Okay, in 2008. Okay, 2018, sorry. Actually, Fagundes also proved for 2 by 2 upper triangular matrices in the general case. Actually, this wasn't his master degree dissertation, which was written in Portuguese. But then a paper with this result was published by these authors with a very more complicated technique. And also they proved here for homogeneous polynomials, again in this algebra, and for arbitrary polynomials with 0 constant term. They have also studied this problem. Okay. For 3 by 3 matrices, I have a result about this in communications mathematics. It's a simple paper, 3 or 4 pages, but the technique used here was not enough to deal with the general case of n by n upper triangular matrices. Other results in this direction are the Jordan polynomials of degree 3 on symmetric upper triangular matrices. The same authors studied skew symmetric elements of Lie polynomials on the skew symmetric elements of here. So I mentioned this to show that there are many approaches to this problem, many different algebras. Okay. So now I'm going to talk a little about the main result here, which is the solution for the general case of this with multilinear polynomials. It's already 11 o'clock, but I started a little late, so I believe I can have about 10 more minutes. Well, the idea is to have a solution to this, the image of polynomials on this algebra. Well, what is the idea here? First, we will need to define this concept of commutator degree of a polynomial. What is the commutator degree? Well, we have this descending chain of t-ideals, the t-ideal generated by one commutator, the t-ideal generated by a product of 2 commutators, and so on. Okay, this infinite descending chain of t-ideals. So if you have an arbitrary polynomial here, then it will fit in some of these t-ideals here and will not fit in the next one. So we say that a polynomial has commutator degree R if it lies here and does not lie in the next one. Okay? This is the definition of commutator degree. It's equivalent to say that F is an identity for R times R matrices, upper triangular matrix, and is not an identity for upper triangular matrix of order R plus 1. Okay. Well, why I am defining this concept here? Because this was already used implicitly in the simplest case when the polynomials of commutator degree 0. What is this? If you consider an arbitrary multilinear polynomial, it can be written this way, indexed by elements of the symmetric group with some scalars alpha sigma here in the field. Okay, and one can easily prove that if the sum of these scalars here is not 0, then the image of the polynomial f is the whole algebra. Okay, you just need to substitute this by, let's say, let's call gamma the sum of sigma. You define x1 by this, and the others by the identity matrix. Everyone here will be identity matrix except for the matrix A. So you factor this, which will cancel this gamma, so you get the matrix A. Okay, the substitution gives you exactly the matrix A. Sorry, A is the algebra. Okay. Let's say M. Sorry. You obtain exactly the given elements. So the image is everyone. And you can prove that if the sum it's equivalent, the sum of coefficients is 0 if and only if it lies here. Okay, so if we see here, we are characterizing elements which are here and not here, which are the ones of commutator degree 0. Okay, and this gives us a characterization of elements of commutator degree 0 by only looking at their coefficients. So the idea is it possible for a polynomial of commutator degree R, only looking at its coefficients to know if, for a given polynomial f, is it possible only looking for its coefficients to know if it's a commutator degree, to know what is its commutator degree? And the answer for this is yes. To that, we need to define this set of, it's a little bit complicated, but we need to define this set of permutations in Sn. What we do? So I'm considering a polynomial with m variables, okay? And I'm putting things like this. T1, T1, T2, T2, and so on. Here, I'm considering all permutations in which this element H1, which is one more than the size of this. Before that, we decomposed this set of indexes in this way. This is a partition of this set, okay? So here, what I mean, I'm considering all permutations which takes this element H exactly to this position and takes the first elements to this in some order, the other elements here to this in some order, which I don't know, and so on, okay? When doing this, here, I mean, this set is indexed by k, which is the number of components here, t, which is the union of these guys here, and small t, which is this set here. Okay, so it depends on these three parameters. By defining this, we will consider these coefficients beta, which are the sum of coefficients indexed by permutations which are in that just defined set. So why this is important? With this, we are able to prove this theorem, that for a given polynomial f, the following conditions are equivalent. Okay, the polynomial has commutator degree R, if and only if this happens, or this we already know. And if and only if, for all k smaller than R, and for any t and t, this is 0. This sum here is 0. So this sum must be 0 for any k smaller than R, And for the k equals r, there must be one substitution which is non-zero. With these conditions, we define the set of polynomials with commutator degree exactly r. Okay, and in a similar way as it was done before, we can find the image of a polynomial in this case. So this is a joint result with Ivan Gonzalez from Technological Federal University of Paraná in Brazil, and we show that a multilinear polynomial, for a given multilinear polynomial, the image of f is j to the r if and only if f has commutator r. Okay, to prove this result, we took an element here, and we needed to find C1 and Cm so that this equation holds, right? To do that, we consider the fact that it's a commutator degree, it has commutator degree r. So these elements here were substituted by some specific nilpotent matrices. And the elements from here, which could commute with themselves, were substituted by some specific diagonal matrices. And with this, and using the fact that the field was infinite to solve some polynomial, to find some non-zero substitution of a commutative polynomial, we were able to solve this equation and finally set the problem for n by n upper triangular matrices. Okay, so still the problem of the conjecture of Lvov-Kaplansky, which is the case of n by n matrices, full n by n matrices, is still open, and maybe someone here is interested in studying it. It's a very nice problem. So that's it. Thank you very much for your attention.
Thank you very much. Are there any questions or remarks? No question? If no question,
just one question. Yeah. Thank you for the interesting talk. I would like to know what will happen if you change upper triangular matrices for matrices with some elements equal to 0 and some elements equal to non-zero element on the main diagonal. So instead of full main diagonal, you have few zeros on it and few non-zeros on it. And then it could be interesting to see what will happen.
Yeah, yeah. You have a paper about this, right? About identities of this?
Yes, about identities.
Yeah.
But this is different story concerning the image of a polynomial, but I think some technique could be applicable.
Yeah, I believe so. I don't know the exact answer, but maybe, let's see. Yeah, sorry, I don't know, but it seems that the same technique may be applied to solve this problem. Yeah. Yeah, I believe so.
Yeah, at least could be interesting to see.
Yeah. Thank you. I appreciate your question. I will consider this.
Yeah. So, do you think that we can find the roots of polynomials of a Hiter-Cayley-Dickson algebra using the upper triangular matrices?
Sorry, I didn't understand the first part. If I can find the roots
of polynomials of a Hiter-Cayley-Dickson algebra using the upper triangular matrices.
Cayley-Dickson, sorry.
Yeah, Cayley-Dickson.
I'm using the upper triangular matrices. I don't think so. Yeah, I believe not. But studying the case of image of polynomials in other algebras is also interesting.
But we can use it as a representation of any space.
Upper triangular matrices.
Yeah.
No,
because
not by any space. I don't know. I believe not.
Oh, so is there already any necessary and sufficient condition for we can use it as a representation?
I don't know. I believe not, but I don't know the answer.
Okay. Thank you.
Thank you.
Other question? Or Max? If no question,
I have a question also.
Okay.
Oh, sorry.
Vox. Jose.
Sí. Thiago, can you go back to the characterization of the polynomials having degree commutator degree R?
Yes. Here.
The permutations before the description of the permutations.
Oh yeah.
In the previous slide. So are these shuffles or what? Because I didn't understood the H here. How do you compute them actually?
This H is the set of the size of the here. This is the size of the one less to the size of the one more than the size of the partition. Yes.
Yeah.
We are partitioning our set in pieces. Let's say these of size H1, this size H2, and so on. And these guys are fixed. These guys are fixed. These are the T1, T2.
Yeah.
So these must be fixed. Always the image of the same guy here. But the others here may permute with themselves.
With themselves only. So this is a shuffle.
Yeah, only with themselves. Yeah.
Okay. Yes.
We cannot have this. No.
Yes, this is called a shuffle in the literature. Yeah. I see.
How it's called?
Shuffle.
Shuffle. Oh, okay.
Like with cards, when you have two piles of cards and you can move them between the piles, but not within the shelves. Yeah. Okay. I see. Thank you very much. Very interesting.
Thank you.
Other question or remarks?
No. I have one question.
Okay.
Yes.
Well, when you gave the definition of graded involution,
yes,
you said that star is a graded involution if AG star is a subset of AG for any G in G.
Right.
Well, isn't that condition satisfied for all graded involution? I mean,
this definition and the question, sorry.
Isn't that condition satisfied with every involution?
No. For example, the next example here shows that it's not true. For example, when you consider the elementary gradings, then the degree of a matrix unit equals to GI minus 1 GJ. Sorry. Right?
Yeah.
And then when we apply the degree to this involution applied to this, we get the inverse of the given degree. So it inverts the degree of the component.
Yeah, I understand. Yes. Thank you.
Thank you.
Other question? Look, if no, many thanks for 2-3 speakers of this afternoon for their interesting and nice